Today, in this video, we'll take our discussion on NMR to the next step by a bit. In order to do so, we're going to use pulse instead of continuous radio wave frequency. And we'll see how we can play around with the nuclei magnetic momentum. Then with that, how we explore these spin system over here or the different spin system over there. However big the molecule is, essentially, we are able to get better detailed information about the structure. Again, let's remind ourselves about the active nuclei. Hydrogen 1 and deuterium, they're all NMR active. However, their spin numbers are different. Therefore, we expect them to have different quantum states, and they behave different on NMR. And their frequencies for detection also could be different. And also the carbon-12, it is inactive because the atomic number and the weight number are both even numbers. Therefore, their subatomic particles spins canceling. Thus, there's no nucleus spin. However, we have about 1% of the natural abundance for the carbon-13, which has odd number of mass unit due to the additional neutron. Thus, we can detect carbon. And I mentioned that is a good and bad. It has low intensity because it has low concentration of carbon-13. However, that made the spectrum much simpler without much manipulation of complex signal. They could have been complex signal if they could interact. So if you have this butane molecule, 50 of them, for example, there, when you have about 200 carbons there, only 2 of them are carbon-13, and that's detectable. So in one molecule there are 4 carbons, but in overall 50 molecule, I didn't even finish drawing 50, but if you do have 50 molecules, you can imagine, say this carbon here is a carbon-13, that's detectable. The carbon there is a carbon-13, and that's detectable. The rest are not. And while you have millions of molecules, you eventually have randomly distributed carbon-13 on this first carbon, the second carbon, and the third carbon, and the fourth carbon. So you can detect all carbons in the molecule. And hydrogen, you have about 500 of them in this 50 butane gas molecules, and about 1% is a 50. So you can say each one of the molecule has out of 10, 1 hydrogen has deuterium. That might give some unusual signal, but other than that, the rest of the hydrogens will give you normal behavior of HNMR. Like we discussed before, each atoms that are active, right? The hydrogens and the carbon-13, not all of them, but say this was a carbon-13, then this has a nuclear spin. So the spin has the magnetic momentum, and their magnetic momentum, they're all random because the alpha and beta spin or any direction of spinning, and the location wouldn't make any difference in terms of energy. So distribution for any possible state should be equal. But as you place the sample in external big magnet like NMR machine does, then the sample in that little tube contains lots of these molecules, and those active atoms will start lining up. As they line up, if you give attention to one spin, they're not actually lining up straight. They have a precession going on. So it depends on their spin state. But if you have an alpha spin, you have a precession going this way. Therefore, you are creating overall magnetization going upward, considering all the distribution of the spin during the precession. And if you have a beta spin, you're expecting it going the other way and precess here and creating magnetization going down. However, due to the external magnetic field, alpha feels more stable, which we talked about, without magnetic field, external one, possessing same energy. But now in the magnetic field, alpha is more stable with a stronger magnetic field. The gap increases. Then the population for the alpha increases as you have a more energy gap with a stronger magnetic field, external one. Therefore, you will expect majority of them going for the alpha spin. So I can put a lot of them here now. So the net magnetization for the z-axis positive value increase, while the negative, you have only a couple of them maybe, or not at all, depends on the energy gap. So overall magnetization takes time to get magnetized, but overall you expect that to be aligned with the external one to be overall more stable. However, it is very important for you to apply your knowledge of NMR here. Not all of these hydrogens have a same electron density. Therefore, the magnetic field they feel are not the same. Therefore, their precession frequency are different. So we talked about this a while ago, but Larmor frequency omega is equals to gyromagnetic ratio, external magnetic field. Basically, with a stronger magnetic field, you can deliver to the nuclei through the electron density that's canceling. Then you can have a more frequency. That's why we needed higher frequency for more de-shielded hydrogen, if you remember. And the nuclei that has a different gyromagnetic ratio, this is proportional to, if you remember, amount of the charge, and the inversely proportional to the mass unit. So the heavier atom have a chance to get the lower frequency, but heavier atom might have more charge. So you need to consider them in the more precise equation. However, you can relate them in this way when you deal with fluorine NMR, phosphorus NMR, and so on. And as we discussed earlier, you learned that it's not really just external magnetic field that determines the frequency of each nuclei. That was also after consideration of local magnetic field due to the regular sigma electron or pi electron, or the the benzene ring kind of strong electric current that generates relatively stronger magnetic field against the external one. And the triple bond situation also was slightly different than other double bond cases, and so on. And so the actual magnetic field that reaches nuclei is that a real factor determining the frequency. Therefore, you can imagine the overall magnetization of the whole molecule. However, you should know this consists of many different little, magnetized nuclei that are processing with a different frequency. This hydrogen might have a frequency that's different from this hydrogen's frequency, right? So it's a collection of all those, and they're processing at different rate. And obviously there are a couple down there that are also possessing different precession frequency. However, also they are in the beta spin state. Okay. Then these days in the modern NMR machine, instead of the continuous wave, we are giving pulse. We can give pulse to have each individual spin, but you can say overall, right? 90-degree tilted. We can give 180-degree, whatever angle you want. And in fact, in order to explore the chain, spatial arrangement, relative position of the groups, and so on, you can actually play with those length of the pulse and the other factors in order to relate different atoms better and read the signal that we needed, and that eventually will allow us to connect to the structural information. Therefore, you can think of it as like Z, X, and the Y axis, right? And the total magnetization of the molecule with all kinds of hydrogen spin. For example, if you are doing HNMR, that could have been carbon 13's spins, a summation of the carbon 13's magnetization. But either way, you can think of that magnetization came down to the x-axis instead of z, and then you have coil that can detect the strength of the magnetization. Then you can imagine the total magnetization is aligned on the x-axis, but you still have external magnetic field. Therefore, if you go back to the picture over here or over there, you actually have each hydrogen atoms precessing around as alpha direction or beta direction, and that has been here, right? Therefore, their rotation direction, determined by the external one, has to be repeated here. So these spins here, they will have to choose whether they go alpha way or the beta way. As it does if you have an imaginary plane of x and the y, right? This spin this is the summation of it, but those individual ones start to move this way on the plane or the other way on the plane, panning out. So like on the XY plane, right? They're going like this, and then a minute later, a microsecond later, they will go like this, and then they move like that, and eventually going around. All right, if that happens, as you can see, if you think about the addition of the vectors, these two groups moving opposite direction adds up, ended up to reduce the size of the total magnetization that will be detected by this, right? So it's gonna get reduced. Eventually this will go all the way back, but this will come back this way as they come back around. So it will fluctuate like this. And they're not gonna stay here all the time, but say they take a certain time to come around, and you can give that as period 1, right? Amount of time it takes to make a full circle. That's, we call one of the relaxation time that we play with. Then you can imagine them, they actually go along with the z-axis. They are going like this, and eventually will go back to where it was, because that was more stable, forced by external magnetic field. So it wasn't enough to just panning out in T1 period, but they will have to go back. Therefore, if you consider that motion, as they turn around once, they came back where it was, but it's not same intensity anymore, because if you look at it, they try to go up, so the size of the M0 got reduced. They're not anymore here, right? They went up here. So if you think about the vector, instead of being here, if it went up there, then the x component of that vector of magnetization is less than when this was on the x-axis. So it's going to keep decreasing. So it turned out that the magnetization value, the vector component of x, is following this trend, exponential decrease trend, like this. Therefore, altogether, you can come up with this kind of fluctuation. Coming back, but then become weaker, coming back and become weaker to the original location. Then eventually it will be 0, because it go back to the this overall magnetization. Then this acquisition unit will see no magnetic component on the x-axis. It goes to the 0. This okay, the time it takes to go back this vertical way, we call longitudinal period or relaxation. And when it's going around on the XY plane, we call it transverse relaxation time, which is T1, and that would be T2. And together you come up with this so-called FID, free induced decay. That's the total magnetization's trend while it is going back to the original magnetization state. Then we can have a Fourier transformation of this. Then you can come up with a frequency, and you have a certain frequency there. If that was only one type of a nuclei you are measuring. However, you are dealing with many nuclei, so it's not gonna be, all together running around or going up. They have their own frequency, and then total ones are measured. So the actual FID is gonna be much more complex, like you've seen before with the IR. It's gonna be really complicated signal, but you can still do Fourier transformation to come up with a multiple signal, right? With the multiple different frequencies. This is a common way of describing the process of acquiring the spectrum. You first wait a certain time, delay time. Sometimes it's to magnetize the sample, or this is the time some other multi-dimensional NMR, you are waiting for other manipulation done on the other type of atom, and so on. Then you give a certain length of the pulse, and this pulse includes all the frequencies that present in the molecule, and you give enough of frequency and duration so you can flip them to a certain angle you want. Then you wait a certain time, have them get ready to relax, or to get the maximum intensity of the detection, you wait. And then you saw how the magnetization decays through the relaxation of the two different mechanisms, and you get the FID. Then you get Fourier transform to get the spectrum. Therefore, that spectrum is, again, not just a graph. It is actually a mathematical graph done by formula. So as you deal with the data, you can use mathematical tool to make the data more reliable or more clear, to get the data extracted better. Typically for hydrogen atoms, to have 90-degree rotation of most of the atoms, it takes a couple microseconds. And then you can repeat this hundreds of times, as you can see, in just a few minutes. Then, as you know, hydrogen NMR, those peaks have some number of lines if you have a neighbors. And that happens in this mechanism shown here. As the spin flipped, like you did here with a pulse, right? So after pulse is given, say you have two neighbors of hydrogens, then you expect to have 3 splitted lines when these two are identical. That means these two nuclei create about same magnetization. Therefore, you can influence the neighboring hydrogen with the same intensity. Therefore, when your neighbors have both alpha spin, when they spin around, the influence of that together toward the hydrogen that you are about to measure, right, at certain ppm. In that frequency, the machine is ready to detect. will be influenced by alpha and the alpha. Those are the low energy, meaning slower spin, right? Slower frequency and low energy. And that's gonna give this measuring hydrogen frequency a certain number. Then you have one alpha and one beta when you have two of them, right? Then that frequency together is going to influence this hydrogen different amount. That makes this frequency changes, and that's different from when these two both were alpha and alpha. Then when both are beta, that is going to obviously make different changes on this spin. Therefore, you get three different frequencies. Therefore, those in this different molecule, imagine you have millions of molecules, right? One molecule had alpha alpha, the other had alpha beta, the other had a beta and beta. Obviously, beta beta has a least probability maybe, but I'm not necessarily, because here you already flipped it. So the population is not necessarily all different, right? Eventually it becomes different, but after flip, from here it goes this way and this way, and that's going to be equal, almost. Anyway, this observed hydrogen has now three different frequencies. Therefore, you're gonna acquire the mixed wave of those three different waves, and your FID will have, I cannot mimic well, but three different frequencies mixed up, and then you Fourier transform it. Then your NMR signal for one signal for this hydrogen with the two neighbors should be three different frequencies. Then the results of the influence of these two hydrogens being in alpha or beta gave the difference of the spin angular speed and the frequency. And that is measured over here between the two lines, each as a J3, because the coupling happened through 1, 2, 3 bonds. And that J value typically is around 7 plus minus few. Okay, it could be 14, but it's around 7-ish. But you can have more accurate calculation even, and it turned out that the strength of the interaction, the coupling between these alpha and beta hydrogens are not really proportional to the distance, which means it's not about, magnetic field interaction, pure magnetic interaction. It's not N pole pulse S pole kind of model. It turned out that the J value is, roughly speaking, J0, roughly it is 14 ppm, by the way, for a regular alkane case, and the cosine square theta. The theta is the dihedral angle between the interacting hydrogens. As you know, when you draw a Newman projection, when they are eclipsed like that, you say 1, 2, and 3 behind carbon, and 4 they have a 0 dihedral angle, so your theta equals 0. All right. So the dihedral angle between 1, 2, 3 and this hydrogen, for example, would be theta 120. If you have an anti-hydrogen, that would be 180 dihedral angle. Then you get this kind of a graph predicting the coupling constant, and the lowest possible value happen to be when the dihedral angle is 90 degrees, when they are perpendicular. And you instantly, when you hear this, get the idea, oh, that must have to do with the orbital, right? When orbitals are 90 degrees, they don't communicate. But when you have a 0 degree and 180 degree, like anti or syn relationship, they both have a quite good interaction. You see, when it's 180, it's anti, but their communication, the interaction strength is as good as a 0. They're not always equal. They're normally, there is some factor coming from the distance, so usually the 0 degree one is a little higher than the value from the 180. But, surprisingly, the 180 value is quite big. This is called the Karplus rule. And in order to study deeper about the coupling, we have to understand some orbital quantum mechanical picture. However, this is an exciting fact because this means that if you calculate J coupling constant from the NMR, the gap between the lines in one signal, you know that what angle of those two alpha beta relationship hydrogens are in the structure. Not only they are, syn or gauche or anti in the long or big molecule, you can get much more interesting and important information about the structure. Then we said in earlier video, when we run carbon-13 NMR, say this molecule happened to have a 1 carbon-13, then the carbon-13 has a hydrogen that's active, NMR active nuclei, very close. As you can see, the coupling between them is possible, the J1, right? Because it's a one bond interaction. Therefore, I mentioned that the carbon-13 NMR is weak with a lot of noise going on. If we had this coupling going on, the carbon-13 NMR is fairly difficult to read. However, I said we can decouple carbon-13. That's what you normally get as a carbon-13 in the textbook after removing interaction with the hydrogen. But then how do you remove the interaction? The key idea of the instrumental side is you have your detector like this for carbon-13 frequency. Then you have your signal, the pulse signal, for the coil that generates the pulse, right? For hydrogen. For example, when you are measuring this carbon, your receiver is tuned to this frequency. Then the signal generator is giving the frequency of these hydrogens. What happens is they will be all in one spin state. So while you are giving pulse to measure the FID of the carbon spin, you are keeping those hydrogen in one spin state. Not like out of 3, you can make up 4 different spin states. So when you have them all in one spin state, you have a one state. Therefore, carbon is getting influenced by one neighboring spin state. Therefore, the acquisition is only showing the spin of this M0 of the carbon that you are receiving the frequency of. So the FID will be from that one carbon without coupling with the hydrogen. As you can see, the modern days NMR, I mean, everything was a modern, but relatively late years of NMR machines are actually using the magnetized nuclei and play around that magnetization and trying to observe, or there will be some manipulation of the relaxation mechanism to detect only a certain signal. Okay, we were not allowing the hydrogen go back to the alpha. You all keep them at the beta, for example. So we manipulate the relaxation so we can eliminate the presence or influence of the neighboring hydrogen. That means we were controlling the transfer of this magnetization from hydrogen to the carbon in order to measure pure carbon signal. This is only beginning because we are talking about one-dimensional NMR, hydrogen and the carbon with a decoupled situation. But we can freely make it transfer, intentionally have it transfer from here to there, or here to here, or here. Or we can have influence on not only in the given spin system, but we can have some interaction with this spin system hydrogen to this spin system hydrogen or carbon. So we can see the connection of this unit and this unit, as if you have one amino acid and the other amino acid separated by the amide bond that doesn't have a hydrogen, but you can see what amino acid hydrogen is right next to the which amino acid, so you can connect the data to the sequencing as well. That's the area of the two-dimensional NMR or higher. All right, this is part 1. I have to stop here for magnetization and how the relaxation and the transfer of the magnetization through these mechanisms. And I'll come back with a part 2 soon. I'll see you then.